Trig students. This is our Test 4 study guide. So this is the last study guide before the final exam. You will have a final exam next week, and so you'll get a study guide for that as well. But in the meantime, here is your last regular test study guide. So it's a short little test. There are actually 17 problems on the study guide, but I believe you only have maybe 15 or so problems on the test. So it's not very long, it's not difficult. You will absolutely need your graphing calculator. So let's just go ahead and start. Question 1 has 3 parts. You won't have a multi-part like this on the test, but I thought we would just go ahead and combine some different polar equations all together in one here. So the directions say to identify the type of graph, okay? So, and a picture of the graph. So all you have to do is choose the given graph that you see that represents this equation. So there's 3 polar equations here. The first one looks like this. R equals 8 plus 8 sine theta. So if you look back through your polar equation section, what you'll find is that this really resembles A plus B sine theta. And this, A plus B sine theta, is an example of a limacon. Okay, now there are a lot of different limacons that this could be. But once you look a little further and you take your A divided by B, both A and B are 8. When you divide one by the other, you get a 1. The only limacon that has an AB ratio of 1 is a cardioid. So you would be able to say this is a graph of a cardioid. Then, if you were to look at the graphs that appear on the MyMathLab test, the one that you want is the cardioid that's facing up, and that is symmetric to this y-axis, this pi over 2 axis. And I know that because if you go to your limacon page and you look at the one of this form, the plus means we are facing up, right? And the sine means that we are going to be symmetric to a theta of pi over 2, which is just that positive y-axis. So you're looking at a cardioid that looks like this. Of course, that looks really ridiculous, but on your graphing calculator, you should be able to see that. So if you want to graph this on your calculator, here's what you're going to need to do. Remember, for these polar graphs, you're going to have to go to mode, and you're going to have to do 2 things, radian and polar, okay? So for this number 1, you should be in radian and polar mode, okay? Once you do that, you could go to y equals and put in exactly what you see, 8 plus 8 sine, and then here's your theta. It's this little button here now. It's no longer an X because you changed to polar mode. Graph it. It's going to kind of be hard to see, but if you notice, there's that little crease, the little butt cheek crease, right? And it's pointed up, and so that's the graph that you're going to want, all right? Okay, we go to the next one. This is an R squared graph. Well, the only polar equations that have R squared like this are going to be an A squared, and in this case, cosine 2 theta situation. This is a lemniscate. Okay, so there's 2 different kinds of those. You're going to want the one, because this is cosine, that is horizontal. Remember, these are like the little infinity signs, right? There's just 2 petals. It's an infinity sign. It's going to be 9 units long because you take the square root of that. So it's a real long 2-petaled infinity sign. but that's the graph that you would be looking for, and you would identify it as a lemniscate. So if I go back to R and I put in, remember this is the one where you have to do the square root, put everything under parentheses for that square root, but you're going to have 81 cosine 2 theta. Now I have 2 parentheses to close, and I hit graph, and it doesn't come out perfectly, remember, because of the square root, but you can kind of fill in the blanks that that's what we're looking at, and you would be able to get the right one, okay? And then last but not least, we have this little guy here. And if you look up this form, what you're gonna find is one that looks like this, A cosine n theta. This is a rose, okay? So this one's gonna be a rose. Your A is 7, that just means that that's your petal length. It's gonna be 7. This n tells you how many petals it's gonna have. In this case, there's 2. N is 2, which means that's an even number. So you multiply 2 by that n, and you should have a rose with 4 petals. Okay, well, for a 4-petal rose, you end up with what looks almost like a cross, and that's the graph that you're gonna circle. So if I go back and I try to do that right on here, I'm gonna get 7 cosine 2 theta and graph it. And there we go. Theirs looks a lot better than mine, but there's your 4-petal rose, and the petals are on each axis there. Okay, so you're going to want to be able to tell the name and pick the picture out of the lineup. Okay, you can do that whole thing from just your calculator if you want to. Okay, number 2, let's go into some vectors. Okay, a lot of vector work on this test, heavy into vectors. Okay, this first question says for the following vectors, A, find the dot product, B, find the angle between them, and C, state whether they are parallel, orthogonal, or neither. Okay, first thing we're gonna do then is the dot product, V dot W. Okay, remember with your dot product, we could go ahead and label these. This would be A1, B1. This would be A2, B2, right? Your dot product is going to be both A's multiplied together, and then both B's multiplied together, and you add those 2 products, okay? So A1, A2 plus B1, B2. This is going to give you 15 minus 15. We have a dot product of 0. Okay, well, if you have a dot product of 0, you already know the answer to B and the answer to C. A dot product of 0 means you have an orthogonal situation. That means perpendicular. And anytime you have anything that's perpendicular to each other, that means you have a right angle, which is your angle between them. And vectors like degrees, so this would be a 90-degree situation. Now, if you do want to go ahead and look this over and just prove that situation, you would take cosine of theta equals the dot product times the magnitude of each vector multiplied together. Well, we already know the dot product at 0. You could find the magnitude of each vector, but if your numerator is 0, then your whole answer is going to be 0. But let's go ahead. Magnitude is going to be a squared plus b squared. That means the magnitude of v is the square root of 34. You can't reduce square root of 34. It looks like you should be able to, but you can't. You get a 2 and a 17, okay? All right, let's find the magnitude of W. It's actually the same thing. You're gonna have 3 squared plus 25 squared. Your magnitude is again square root of 34, okay? Well, 0 divided by this is still 0, okay? So we have cosine theta equals 0. That means that we take second cosine of 0 in your calculator. Now, remember, this should be degree mode. Okay, degree mode is what we're looking at for vectors, and it'll say that on MyMathLab. Okay, second cosine of 0 is going to give you 90 degrees, which is exactly what we thought. So with a dot product of 0 and an angle between them of 90, you have two orthogonal vectors. So if this were 180 degrees and this was some other number, you would have parallel. And then if both of those things were just some random value, then it would be neither, okay? All right, number 3, let's find the magnitude of V. So we have another vector here. Here's our A, here's our B. We talked about the magnitude up here already. We said that the magnitude of a vector is the square root of a squared plus b squared, and we only want the positive value. So I'm going to have 5 squared, that's 25, plus -1 squared is just 1, and I get the square root of 26, which cannot be reduced. That's a 2 and a 13, and that just does not reduce down. All right. Moving right along here, number 4. Find the quantity 6V plus 7W, and then it gives you V and it gives you W. So first thing we want to do is find 6V. So we're going to take 6 and we're going to multiply it by the vector V. So we're just going to distribute that 6 through there, and we get 42I minus 54J. Then we'll find 7W. We'll take 7 and we'll distribute it through there, through W. We get -42I plus 28J. Then last but not least, we're going to add them together. So I'm going to have 42I minus 54J plus a -42I plus 28J. Now, it just so happens the I terms cancel. We combine these J terms, and I got 26J as my answer. Okay, make sure you can see that. There we go. Okay, let's look at number 5. Now, number 5, you already know the answer to because we covered it on that last page. Okay. If two non-zero vectors, V and W, are orthogonal, remember that means perpendicular, then what is the angle between them? Okay, so I know I told you that vectors like degrees, but MyMathLab is difficult, and you know that. And I can't remember if it wants the answer in degrees or radians, so it's going to tell you on there. I have a feeling it's radians. But we're going to write both. So orthogonal is perpendicular. The angle between them in degrees is 90 degrees. In radians, if you remember what 90 degrees is equal to, that's pi over 2. And I think pi over 2 is what you're looking for that problem, but you'll have to check. Okay, number 6. Write the vector in the form AI plus BJ, given its magnitude is 20, and the angle between it is, or the angle it makes with the positive x-axis is 120 degrees. Okay, what you're looking for then is this formula, the magnitude times cosine alpha I plus sine alpha j. Okay, so we're looking at 20, that's our magnitude, I'm just plugging in here. Cosine 120 degrees I plus sine 120 degrees j. Okay, now we have to keep going because we want it in this form. So that's where our unit circle comes into play. We look at 120 degrees. Here's our cosine, -1/2, here's our sign, positive root of 3 over 2. We're just going to replace them in here. So we have negative 1/2 I plus root of 3 over 2 j. Okay, now we're going to distribute this 20 through there. I'm going to get negative 10I plus 20 root of 3 over 2j. Now we can still reduce this, so keep going. There's your final vector, just like that. Okay, that's your answer. All right, number 7 says find A, here's A, so that the vectors v and w are orthogonal. Okay, so remember what orthogonal means. That means the dot product of them is equal to 0. Okay, so if I'm looking for A, then what I'm going to do is find the dot product. Okay, so it's going to be this first component, which is 1, times this first component, which is negative 2, plus the second component, which is negative A, times the other second component, which is negative 3. Now we know the dot product itself is supposed to be 0, so I'm going to replace that side with 0. This is negative 2 plus 3a, because a negative and a negative make a positive. Now I just have a nice little linear equation. I'm going to add 2 to both sides and divide by 3. And my answer is 2/3. Okay. All right. Number 8. We have a vector v. It has an initial point of P and a terminal point of Q. I want you to write it in this form and find its position vector. Well, the position vector is just Q minus P. That's it. So if I'm trying to find vector v, I'm going to have 5 minus negative 6. That's my I component. Negative 7 minus negative 8. That's my j component. So I'm just subtracting that first component of each, subtracting the last component of each. This is going to give me 11i plus 1j, or just j. That's the position vector. Okay. All right, so I hope you're finding this pretty easy. It's definitely the easiest trig test for sure. All right, let's move on. Look at number 9. Okay. Got a little blurry there. Has it been blurry the whole time? I hope not. Let's see, let me clear that off a little bit. Sorry guys. There we go. Okay. I don't know why it got blurry. I guess because I changed the page. Okay, so find the direction angle of V for the following vector. Okay, well, anytime we're finding direction angle, we have to be mindful of our quadrants. So if I were to just make a little quick and dirty picture here, and I were to get the components, you know, the X, Y, or A, B, whatever you want to call it, components, what I'm looking for is the vector like that. Now remember, these little funky things, these are just in the place of parentheses, vectors like these little things. All right, so I have a negative X component and a positive Y component, which puts me in quadrant 2. Now that's helpful because when I go to find my angle, I want my angle to be in quadrant 2. So this is my X, so to speak, and this is my Y. The angle that I want, they like to call it alpha, would be tan alpha equals Y over X. Okay, so my tan alpha is going to be 5 over negative 5 root of 3. If I reduce that, I get negative 1 over root of 3. Now, I don't have to rationalize that. It's actually easier for me to just leave it for a minute. What this means is that I want to know for what angle alpha in quadrant 2, okay, I'm only looking in quadrant 2 now, for what angle in quadrant 2 is tan equal to -1 over root of 3? Okay, that's what I'm looking for. Well, if I take my unit circle and I'm looking in quadrant 2, I have 3 choices for my degrees, right? And this is what it wants it in degrees. I have 3 choices. It's not going to be 135 because the tangent of 135 is -1. Y over x, that would be -1. That means it's got to be one of these two. And again, look at the placement of the root of 3. Okay, if we go back, the root of 3 I have is in the denominator, okay? So if I want the root of 3 in the denominator, and I know tangent is y over x, if I choose this one, y goes to the top with its root of 3. If I choose this one, the x goes to the bottom with its root of 3. This is the one that I want, okay? And that's 150 degrees. So there we go. So remember that what that means is this is the point, right? So if I were to take for tangent, I would have y over x. My 2's would cancel, and that's where I get that value right there. And that's why sometimes when you're doing this, it's easier not to rationalize so that you actually see the raw tangent before you start manipulating it. But that's the angle in degrees that we want. Okay, now we're going to start going back and forth. We're going to stop with vectors. That's all your vector material. And we're going to go back and forth between polar equations and rectangular equations. So remember, rectangular equations involve only x and y. Polar equations involve r and possibly a theta. Okay, so here we go. We want to rewrite this, okay, as a rectangular equation. I'm sorry, this is rectangular, it's got x and y. We want to rewrite this as a polar equation. Okay, so what I see right away is I have a GCF on this side of 7. So if I pull out that GCF, that's what I end up with, okay? Now, I recognize y squared, or x squared plus y squared, because that's what r squared equals. So I'm going to replace that with r squared. Then I'm going to solve for r squared. I don't have to solve for r, just r squared. And that's my polar equation. That's all I had to do. I just had to get rid of my x's and y's and get my r on a side by itself. Okay. All right, this one is already a polar equation, and it wants us to make it rectangular, and there's another step here. Then identify and graph the equation. Okay, well, it just so happens that this side over here, this r sine theta, I know what that equals. That equals y. I can replace this entire left side by y, and suddenly I have a rectangular equation. I also recognize that equation. Anytime all you have is y equals something, that's a horizontal line, okay? And then if I were to pick out the graph, I'm going to pick out the graph, 1, 2, 3, 4, 5. That looks like this with a horizontal line at y equals 5. So here's the 3 parts. Here's the equation, I identified it, and I have the graph, okay? All right, so easy enough. Let's look at number 12. Okay, 12 does not want me to graph. It just wants me to change this to a rectangular equation. That's it. Okay, this one's a little difficult. Okay, it has r equals 7 sine theta. Well, If I were to switch this to rectangular, and I see sine theta, it sure would be nice if there was an r right here, because r sine theta is y. Well, how do I get an r right here? Well, I can put one there, but then I'm going to have to put another one over there too. So the key here is multiply both sides by r. That's the key. So I'm going to get r squared on the left and 7r sine theta on the right. Now remember what r squared equals: x squared plus y squared. Okay, remember what r sine theta equals: y. All right, now we want all these x's and y's on the same side. So I'm just going to subtract 7y, set it equal to 0, and there's my rectangular equation. That's easy enough. All you have to do. All right, 13 is back to what, just like number 11, what 11 wanted. It wants you to write this with rectangular coordinates, then identify it, then graph it. Okay, well, I recognize r cosine theta. That's x, just like r sine theta was y. So if I replace the left with an x, suddenly I'm done. If I were to identify this, that is a vertical line. And if I were to graph it or find the graph, I have a vertical line right there at x equals -4. Okay, easy enough. Now, number 14 wants you to plot this point that is given in polar coordinates. Well, remember, polar coordinates look like this, which means my r is -4 and my theta is -5 pi over 3. And remember that you want to graph your theta first. That's the first thing that you want to do. Okay, well, what in the world is -5 pi over 3? Well, I think it's easier to go to the unit circle. Here's +5 pi over 3, which is really 300 degrees. So if I were to start here and go counterclockwise, that's where I end up, +300 degrees. Well, this wants me to go negative, which means I'm going to start here and go clockwise 300 degrees. I end up at 60. I end up right there at 60, okay? So I'm really looking at a +60 degrees or + pi over 3 degrees, and then a -4, okay, on here. I think I graphed you the wrong way. I did. My answer is wrong on there. Sorry, guys. Okay, a +4 would put you right here. A -4 is going to put you down here. So the answer in the back is wrong. Sorry, sorry, sorry. Because this is -5 pi over 3, and in the back I went 1, 2, 3, 4, and I marked it right there, but this is a negative. I just caught it. So 1, 2, 3, 4. I had to move backwards, -4, and that's where I am, is right there. That's really strange. I'm gonna have to go back and kind of take a peek at that one, but that's what we're looking at there. So I apologize. Okay, make sure you guys can see that one. All right, 3 more. Here we go. Okay, 15. 15 and 16 are the same directions. You have a complex number in polar form, and it wants you to write it in rectangular form. All right, well, here's the thing to remember. This number out front, this coefficient, is r. This angle that you see appear twice is theta. we're trying to write this with only x's and y's. So remember, x is r cosine theta, y is r sine theta, okay? So what we're dealing with is 14 cosine 5 pi over 3. Y is going to be 14 sine of 5 pi over 3. Okay, so x is going to be 14. Here's our 5 pi over 3. Cosine is 1/2. Sine is negative root of 3 over 2. Okay, here we go. So we're going to have 7 for x. Y is going to be negative 7 root of 3. When we write that in rectangular form for a complex number, which remember is like a plus bi, we get 7, minus 7 root of 3 I. And there we go. All right, we want to do the same thing for this one. There's my r, there's my theta. X is going to be r cosine theta. Y is going to be r cosine theta. Okay. All right, now we need to know, what is 3 pi over 2? Well, remember, 3 pi over 2 is down here. It's 270 degrees, so my cosine is 0, my sine is negative 1. So x equals 0, y equals negative 6. Here's the form I'm looking for, so I would have 0 minus 6i, but negative 6i is all you want. You don't have to worry about that 0. Okay. All right, guys, last but not least, very last problem. This one is the longest problem that you have, but then this is it. Okay. So we want to plot this complex number on the complex plane. On the test, you're just going to have, I do think you have to put the dot on there the more I think about it. I can't remember if you have to identify it or graph it, but anyway, we'll do that. Then we're going to have to write it in polar form and then also write it in exponential form. Okay, so let's plot first. So what we have here is we have an x, or a real part, of 12 root of 3. Okay, well, just so you know, 12 root of 3 is actually 20.78. Okay, we have a y, or an imaginary part, of negative 12. Now, I could not find a larger complex plane than this. So we're just going to kind of get rid of these numbers that you see here. Okay. And, well, I'm going to leave these here. Sorry. Okay. And I'm going to make these on the positive real axis 2 tick marks of 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, and this last one, 20. Okay. And then I'm just going to extend this negative imaginary one, negative 10, negative 11, negative 12. Okay. So if I go positive real 20.78, I'm about here. Imaginary negative down to 12. This puts it at right there. And that's in quadrant 4. So that's your plot. That's all you have to do is put your dot in there. Okay. Now we want to write this over in polar and in exponential form. Okay, so we already said x is 12 root of 3. We said y is negative 12. Okay, here we go. So we're going to need an r. This actually, before we get going, let's write what those forms are. Your polar form is r cosine theta plus I sine theta. And your exponential form is z equals e to the I theta. Oh, I forgot my r. Okay, can you tell I'm just exhausted? There you go. Okay. All right, so let's find an r first. Our r is going to be the square root of x squared plus y squared. Okay, here's my x, square it. Here's my y, square it. Okay. So 12 squared is 144. Square root of 3 squared is 3. 144 times 3 is 432 plus negative 12 squared is 144. Add those together, you get the square root of 576, which, believe it or not, is a nice little r of 24. Okay, now we're going to need theta. All right, so we know that tan theta is y over x. So my y is negative 12, my x is 12 root of 3. That's going to reduce down, well, that looks familiar, doesn't it? To negative 1 over the square root of 3. Okay, and we already said we want to be in quadrant 4. We got that from our graph. So we are looking for what theta in quad 4 does tangent equal negative 1 over the root of 3. Okay, here's quad 4. We know it's not this one. Tan would be negative 1. We're looking for a root of 3 in the bottom. So if tangent is y over x, we want our x to have the root of 3. That would put it in the bottom. And here we go. 11 pi over 6, because we want radian measure, would give us y over x, which would give us what we want. So theta equals 11 pi over 6. Now we're